Hello there. I'm glad you made it here. Let the day loosen its hold, shoulders soften, jaw unclench, and your breath find an easy, even rhythm. You don't need to solve or remember anything. Just rest while we drift quietly into the dark. Tonight, our lantern is the Phoenix Cluster, an immense city of galaxies gathered in a sea of hot, glowing gas, more than 5 billion light-years away. We'll move unhurriedly through its quiet architecture, filaments feeding the core, old red giants and newborn blue stars sharing the same address, a supermassive black hole turning gravity into light and long, slender jets. The science will settle in like a warm blanket, dark matter's scaffold, cooling flows and feedback, X-ray halos and radio bubbles, gentle, steady, sleep, safe. If these calm journeys help you unwind, a soft tap on like and subscribe is a small kindness that helps other sleepy travelers find their way here. For now, let the room dim, let the breath deepen, and imagine a distant cluster suspended in night. Thousands of galaxies drifting together, gas breathing in slow tides, and light that began its trip when our world was young. Close your eyes if you'd like. We'll begin our unhurried walk through the Phoenix Cluster, where the universe writes quietly, and everything moves at the pace of rest. Far beyond the reach of our familiar constellations, deep within the faint outline of the Phoenix, there drifts a structure so immense it humbles imagination itself. More than 5 billion light-years away, it glows like a quiet ember in the endless dark, the Phoenix Cluster, a congregation of thousands of galaxies drawn together by the slow, patient hand of gravity. Around them, a sea of superheated gas shimmers in silence, a halo of invisible fire. At its center burns something extraordinary, the brightest cooling flow ever seen, where gas condenses and collapses into new stars at a rate that seems to defy the limits of physics. It is not merely a cluster of galaxies, but a vast workshop of creation matter remade in the dark, light born again from its own fading heat. From our small and fragile world, we gaze outward through layers of distance and time. The stars closest to us flicker as familiar patterns, their light crossing only a few years of space. Beyond them, galaxies drift, tiny islands of brilliance, whose glow began its journey millions or billions of years ago. Each photon that reaches us carries a memory of how the universe once looked, a whisper from an earlier age. What we call the observable universe stretches outward in every direction, a sphere tens of billions of light-years across. Its edge is not a wall, but a horizon defined by how far light has managed to travel since the beginning of time. Within that vastness, matter is not evenly spread. It gathers into filaments and sheets, delicate threads of brightness, forming what astronomers call the cosmic web, the great invisible scaffolding of dark matter. Where those filaments cross, clusters like the Phoenix are born, immense knots of gravity where galaxies collect, orbit, and evolve together. In that crowded heart of space, thousands of galaxies move in a slow celestial dance, each one a home to hundreds of billions of suns. Between them, hot gas flows and collides, heated to tens of millions of degrees. It glows in X-rays, invisible to our eyes but radiant to the instruments that watch from above Earth's atmosphere. This gas, heavier than all the galaxies combined, fills the cluster like a luminous ocean of energy. The Phoenix Cluster contains almost 1,000 trillion times the mass of our Sunday. That gravity bends not only the orbits of stars, but the very fabric of space-time itself. Light from more distant galaxies curves around it, magnified and distorted. painting subtle arcs across the deep sky, a cosmic lens revealing the universe beyond. In astronomy, distance is also time. To look at the Phoenix cluster is to look back more than 5 billion years into an era when Earth was still young and the solar system was just beginning to find its shape. The light that reaches us tonight began its journey then, stretched thin by the universe's steady expansion. This stretching, what we call redshift, tells us how long the light has traveled and how much the cosmos has grown since it began. For Phoenix, that redshift is about 0.6, meaning we see it as it was when the universe was barely 60% of its current age, an age when the great structures of matter were still coming together, learning the rhythm that still guides them now. To glimpse something so distant requires many eyes working together. Telescopes on mountaintops catch the faint shimmer of its galaxies. Infrared instruments peer through dust to trace the quiet birth of stars. Radio antennas listen for the faint hum of charged particles spiraling through magnetic fields. Yet it is through X-rays that clusters like Phoenix truly reveal themselves, their invisible heat transformed into light that only space telescopes can see. In those wavelengths, the Phoenix cluster blazes. Observatories like Chandra and XMM Newton have mapped that glow in exquisite detail, charting the pressure and temperature of the gas, the shape of the gravitational well, the restless motion within. Among thousands of clusters catalogued, Phoenix shines with a fierce, improbable brilliance, an island of creation where energy and matter meet at the edge of balance, and the universe itself seems to breathe a little faster. The universe that cradles the Phoenix cluster moves to the rhythm of only a few quiet laws. 4 great forces weave through everything: gravity, gentle yet patient, shaping galaxies and clusters across unimaginable distances; electromagnetism, drawing atoms together, kindling light, sculpting the elegant arcs of charged particles; the nuclear forces, hidden in the heart of every atom, holding the smallest things together and feeding the fire of stars. From their conversation, everything arises: the dust of planets, the glow of nebulae, the whirls of superclusters stretched thin across space. The Phoenix cluster is a place where these forces meet in rare harmony, a living laboratory where the universe experiments with scale. Galaxies drift and merge like slow tides. Gas flows between them, stirred by the deep gravity well and the breath of supermassive black holes. Stars ignite and fade, their birth and silence governed by the balance between heat and cool, motion and rest. What appears from afar as a single blur of light is, up close, a delicate ecosystem, an interplay of violence and grace that connects the smallest seeds of atoms to the grandest architecture of the cosmos. Every strand of light that reaches us from that distant cluster carries memory. The X-rays tell of searing gas, thin and hot as thought. Optical light traces the quiet pulse of stars. Infrared waves reveal warm dust, glowing with the energy of new suns. Radio whispers mark the presence of magnetic fields, invisible yet real as breath. Together, these wavelengths create a chorus. When astronomers weave them, they transform scattered photons into story, an image of how the cluster lives, how it changes, how time itself unfolds within it. To grasp its true size, one must surrender ordinary measure. A single galaxy, vast and crowded with stars, becomes only a point within the cluster's embrace. The space between galaxies, distances that would take light millions of years to cross, is small compared with the luminous gas that fills the void. The heat of that gas outshines imagination. The energy required to sustain it surpasses the output of billions of suns burning for billions of years. Yet the source is simple: gravity. Matter falling inward, giving up potential for light. Over eons, this quiet sacrifice sculpts the cluster into what we see now, a monument shaped by falling and yielding, by balance found through motion. Seen from Earth, the Phoenix cluster is only a faint smear among countless others. To the eye, nothing announces its grandeur, but the patient instruments of astronomy decode its language. Spectra reveal its distance, images show its crowded galaxies, X-rays uncover the hidden halo of hot gas. Bit by bit, a blur becomes a structure becomes a story, and that story becomes a reminder. The universe hides its wonders in plain sight. Every dim point in the dark holds the potential for revelation. The same laws that guide this distant cluster shape everything we know. The pull that drops an apple to the ground is the same gravity that binds galaxies. The force that holds the nucleus of an atom together is cousin to the one that drives the fusion in stars. Across all scales, nature hums in one key, the music repeating from microcosm to macrocosm. The Phoenix cluster, though unimaginably remote, belongs to the same order, obeys the same rules, and burns with the same kind of light that warms our own sky. Long before it existed, the universe was smooth and quiet, a haze of hot plasma, almost uniform. Then, in tiny fluctuations, gravity found its voice. Slightly denser regions pulled in matter. Those regions grew denser still. Over millions of years, they gave rise to the first stars and galaxies, the first filaments of the great cosmic web. Over billions, the web thickened, and its nodes, clusters like Phoenix, became the great cities of matter we see today. The Phoenix cluster is one of the elder monuments of that long evolution, a mature creation of a universe that builds patiently, particle by particle, until vastness itself becomes an art. The birth of a galaxy cluster is not a gentle event. It is a story written in heat and motion. As galaxies fall inward toward the growing well of gravity, they gather speed thousands of kilometers each second, their momentum carved into the dark. When they strike the vast clouds of hot gas already waiting there, the collisions send out ripples of energy that travel like thunder through space. Shock waves bloom, compressing and heating the gas until it glows in X-rays, a silent brightness that only the instruments above Earth can hear. Over time, this chaos learns balance. Gravity pulls inward, pressure pushes outward. The Phoenix cluster, like a vast cosmic heart, beats between those two forces. But no balance in the universe is ever still. New galaxies continue to fall in, older ones merge and transform, and the black holes at their centers pour energy back into the gas around them. In this way, the cluster never stops becoming. It shifts, adjusts, breathes. At the center of it all lies a single enormous galaxy, luminous and ancient, the gravitational anchor that holds the cluster's weight. Within its quiet core is a thing both invisible and absolute, a supermassive black hole, billions of times the mass of our Sunday. It does not shine, yet its presence defines everything nearby. Gas drawn toward it spirals faster and faster, until friction turns motion into light. Around it forms an accretion disk, bright enough to outshine whole galaxies. From its poles, jets of plasma roar outward into the cluster, stretching across hundreds of thousands of light years. This is feedback, the black hole's way of shaping the world around it, heating the gas, regulating the birth of stars, deciding how much creation the cluster can bear at once. In most galaxy clusters, This feedback keeps the gas too warm to condense. It acts like a cosmic thermostat, halting the cooling before new stars can form in great numbers. But the Phoenix cluster breaks that rule. In its depths, despite the black hole's power, the gas cools faster than it can be reheated. The result is astonishing. A stellar nursery blazing with new life, creating more than 700 suns worth of stars each year. No other cluster known forms stars so quickly. For a brief window in cosmic time, the cooling has outrun the heating, a delicate imbalance that turns catastrophe into creation. Astronomers uncovered this secret by weaving together light from every corner of the spectrum. In optical and infrared images, the central galaxy shines with knots of brightness, young stars still wrapped in dust, their light scattered and warm. Radio telescopes pick up the faint hum of synchrotron radiation, traces of supernovae and high-speed particles spiraling through magnetic fields. X-ray observatories show a dense, radiant core where gas cools and condenses. Each wavelength adds a piece to the puzzle, and when they are overlaid, the picture reveals a truth more vivid than expected. The Phoenix cluster is not merely glowing, it is growing. In its crowded heart, the gas radiates energy so rapidly that it cannot maintain its heat. As it cools, it sinks toward the center, becoming denser and cooler still. This runaway process is known as a cooling flow, a cascade that feeds itself. Usually, the black hole interrupts this cycle, stirring the gas and keeping it from falling too far. But here, for reasons still studied and debated, the cooling has the upper hand. Rivers of gas collapse into clouds, and clouds into stars. The cluster becomes a frozen moment in cosmic evolution, a rare glimpse of transformation mid-breath, where the universe is caught between its need to burn and its need to rest. Its name, Phoenix, is fitting. It sits in the constellation that bears the same myth, and it lives up to the story. From its own heat, it creates new light. From its exhaustion, renewal. The hot gas that should mark decay becomes the cradle of new suns. It rises again and again, its cycles of heating and cooling, echoing the mythic bird that remakes itself from fire. Here, destruction and creation coexist, partners rather than opposites. The black hole both nourishes and restrains. The gas both feeds and resists. What results is not chaos, but conversation, a slow negotiation between forces that never truly end. For astronomers, the Phoenix cluster is not simply a place to observe. It is a teacher. It shows what happens when cosmic balance wavers, when feedback falters, and when the quiet machinery of the universe turns briefly, gloriously, inefficient. It reminds us that even equilibrium must occasionally give way to growth. Yet for all its radiance, the cluster is not kind. The gas within it burns at more than 30 million degrees, hot enough to vaporize any solid material in an instant. Radiation streams through it, dense with high-energy particles and cosmic rays. To any form of life like ours, it would be a lethal sea. But tucked inside the galaxies that orbit this blazing core, billions of stars move in relative calm. Around some of them, perhaps, planets circle quietly, bathed in their own small light, unaware of the inferno that surrounds them. The cluster holds within it both the most violent and the most tranquil realms imaginable, fire and silence sharing the same vast address. When we look at it from Earth, we do not see the cluster as it is, but as it was. The light that reaches our telescopes tonight began its journey more than 5 billion years ago. It left before life on Earth had taken form. before the continents settled, before our sun had finished shaping the system we now call home. During those long years of travel, stars were born and died. Galaxies collided and merged. The universe stretched and thinned. Yet the light endured, carrying the memory of the cluster through the expanding fabric of space. What we see is a fossil of motion, a frozen instant in a dance that has never stopped. The Phoenix cluster today is not the one whose light we receive. Its galaxies have drifted farther, its stars aged, its gas reshaped. But this distance in time does not diminish it. It gives it depth. Each photon is both messenger and relic, a piece of ancient fire that now lands softly in our instruments. Through them, we look not only outward, but backward, and perhaps inward too, into the steady truth that everything, from stars to lives, exists in motion, always changing, yet somehow still connected. In the quiet between thoughts, when the mind begins to drift, imagine that immense cluster suspended in darkness, its galaxies like embers, its gas like breath, its black hole whispering gravity into the void. It is a place of fire that births light, of order that grows from turbulence, of endings that continually begin again. The Phoenix cluster reminds us that the universe is patient with paradox, and that even in its fiercest heat, there is the promise of renewal. The story of the Phoenix cluster is also the story of how faint light becomes knowledge. From a handful of photons gathered by patient instruments, astronomers have conjured distance, mass, temperature, composition, and time. They have traced the pathways of gas and galaxies, measured the pulse of the central black hole, and rebuilt, in careful thought, a system that lives billions of light years away and billions of years ago. It is one of the quiet triumphs of the human mind, that with mathematics and imagination, we can reach across the void and touch the shape of what once was. Every number derived from that light is a translation of something ancient. The photons have traveled through expanding space, stretched and thinned until their message barely remains. Yet from them, the mind reconstructs motion, energy, and scale, a language written in radiation, decoded by reason. It is a kind of alchemy, this transformation of starlight into understanding, and it shows that the universe, however immense, can still be read. The Phoenix cluster stands as one of the great volumes in that cosmic library. Within it, thousands of galaxies orbit in a haze of superheated plasma. A supermassive black hole at its center feeds on falling matter, radiating energy across the spectrum. Around it, the gas cools, condenses, and forms stars at rates that challenge our sense of balance. It is a stage where the laws of physics are performed on the grandest scale: gravity, heat, radiation, and time, weaving together to create a harmony of motion that spans millions of light years. In its light, stretched thin by cosmic expansion, we see a younger universe still in the act of construction, laying down the scaffolds of galaxies and clusters that would one day give rise to us. The Phoenix cluster is both distant and intimate, a mirror held up to the processes that shaped our own home, a reflection of the forces that have always worked in silence to build the worlds we inhabit. At its heart lies a galaxy, unlike any other near us, a giant elliptical that dominates its surroundings, known simply as the brightest cluster galaxy. It is massive beyond comfort, a system that has swallowed smaller companions over billions of years until it became the gravitational center of the entire cluster. Its structure is smooth, spheroidal, its light red with age. Most of its stars were born when the universe was young, their fuel long since exhausted. What remains glows softly, like embers beneath ash. This kind of galaxy is the product of slow consumption. As galaxies wander through the cluster, they lose energy through gravitational interactions, a process called dynamical friction. Over time, they drift inward, merging with the central giant. Each collision adds new stars to its growing mass, a process astronomers, with a hint of poetry, call galactic cannibalism. The result is a behemoth containing trillions of suns' worth of stars, its ancient light smooth and red, its shape the patient outcome of billions of years of quiet accumulation. But the Phoenix Cluster's central galaxy refuses to stay old. Around its core of elderly stars, a new radiance has bloomed, a ring of brilliant blue light, the mark of vigorous star birth. Spectra show the glowing fingerprints of hydrogen and oxygen, gases excited by the ultraviolet blaze of young stars. Infrared observations reveal filaments of warm dust, each one a cradle of formation. Against the red calm of the old population, this youth burns startlingly bright, a rebirth at the heart of an ancient body. In these regions, stars are not forming gently. The dense clouds of gas produce giant stars tens or hundreds of times more massive than the Sunday. They burn through their lives in a few million years, brilliant and brief, before ending as supernovae. Each explosion floods the galaxy with shock waves and heavy elements, stirring the gas, compressing it, and sometimes triggering yet more rounds of star formation. It is a feedback loop of creation and destruction, an accelerated heartbeat that will last only as long as the fuel remains. Eventually, the cold gas will be gone, and the galaxy will return to quiet. But for now, it is in full bloom, a rare moment when a massive elliptical becomes once again a nursery. The contrast is striking, an ancient structure wrapped in new light, as if time itself had reversed for a moment. Seen from afar, the galaxy still looks smooth, a soft glow that fades gently with distance. But closer inspection reveals a more intricate landscape. Filaments of gas stretch from the core, tracing the flow of cooling material as it falls inward. Bright knots mark clusters of newborn stars. Dark lanes of dust thread through the light, remnants of the clouds not yet consumed. The result is not symmetry but movement, a galaxy in the midst of becoming, its calm surface hiding a restless interior. Its stars span every age. Most are relics of the early universe, 10 billion years old or more, their light cooled to a steady red. But scattered among them are regions of brilliant blue, young stars shining with the intensity of youth. Their ultraviolet light ionizes the gas, creating glowing ribbons visible across the spectrum. By comparing the light from these two populations, astronomers can reconstruct the galaxy's history, reading how it grew, paused, and flared again through cosmic time. At the galaxy's very center sits one of the most massive black holes ever measured, a gravitational abyss weighing billions of suns. Around it, stars orbit at impossible speeds, their motion betraying the presence of something that cannot be seen. Gas that drifts too close is captured, spiraling inward through the accretion disk. As it falls, friction and compression convert motion into heat and heat into light, flooding space with radiation from radio waves to X-rays. What begins as silence becomes brilliance. What falls into darkness gives rise to luminosity. The black hole's influence extends far beyond its edge. The energy it releases stirs the surrounding gas, preventing it from cooling too quickly. It acts as both governor and guardian, regulating the pace of the galaxy's evolution. Normally, this balance holds steady, heating and cooling in rough agreement, star formation kept in check. But in the Phoenix cluster, that agreement has faltered. The gas is cooling faster than the black hole can reheat it, leading to an outbreak of star formation unlike anything nearby. Something, perhaps a recent merger, perhaps a fresh stream of matter drawn from the cosmic web, has tilted the balance. This moment will not last. In cosmic terms, it is a blink, a brief flare, before the system finds equilibrium again. But it is enough for us to witness. Through it, we see how fragile balance can be, how quickly the universe can pivot from stillness to creation. The Phoenix cluster's central galaxy shows both extremes at once. An ancient heart surrounded by the fever of youth, gravity, and heat, locked in their endless dialogue. To imagine it is to hold two truths at once. Within a single galaxy, time moves at different speeds. The outer stars linger in the long evening of age, while the inner regions blaze with the dawn of renewal. In that contrast lies the beauty of the cosmos, a reminder that nothing ever fully ends, that even in exhaustion there waits the spark of rebirth. The Phoenix cluster, patient and luminous, carries this lesson across billions of years, whispering through its light the quiet promise that from the ashes of what was, something new always rises. Surrounding the radiant heart of the Phoenix cluster lies a halo no eye can see. It is not made of stars or dust or gas, but of something silent and invisible dark matter. Though it gives off no light, its pull shapes everything that shines. This hidden scaffold extends for hundreds of thousands of light years, far beyond the reach of the galaxy's visible edge. It holds more mass than all the stars and gas combined, binding the system together with gravity's unseen thread. Astronomers trace its presence by listening to motion rather than light. They measure how stars and clouds of gas move, how their speeds shift as they orbit the cluster's core. From those patterns, they reconstruct the shape of the dark halo, mapping what cannot be directly observed. The result reveals a vast gravitational basin, a deep well in space-time itself, with the central galaxy resting at its lowest point, like a pearl held in the palm of an invisible hand. Threaded through this immense system are magnetic fields, stretched and twisted by the motion of charged particles in the hot gas and by the ceaseless turning of matter around the black hole. These fields act as cosmic currents, guiding the flow of plasma, shaping the accretion disk, and steering the twin jets that emerge from the black hole's poles. Radio telescopes pick up their whisper, the synchrotron glow created when electrons spiral along magnetic field lines at nearly the speed of light. What appears calm, invisible light is, beneath that calm, alive with invisible tension, electricity, and magnetism entwined in the galaxy's breath. Fueling the galaxy's restless brilliance is an immense reservoir of cold gas. Once part of the cluster's hot atmosphere, this gas has cooled through radiative emission, condensing into clouds only a few degrees above absolute zero. Within these molecular sanctuaries, composed mostly of hydrogen, laced with traces of carbon monoxide and heavier elements, the seeds of stars are waiting. The mass of this cold gas exceeds 10 billion suns, enough to sustain the galaxy's furious rate of star formation for tens of millions of years. And because the hot gas of the cluster continues to cool, this reservoir is constantly replenished, a steady river feeding the galaxy's interior. Within the dense molecular clouds, gravity negotiates with turbulence, pressure, and magnetic force. Where gravity wins, a region collapses inward, fragmenting into smaller knots that will each become a star. The most massive of these form first, devouring their surroundings with speed, their gravity fierce enough to pull the nearby gas into dense spirals. These newborn suns ignite with ultraviolet fire, ionizing the gas around them and sculpting glowing shells of hydrogen, the nebulae we call H2 regions. Supernovae soon follow, their shock waves sweeping through the galaxy, scattering heavy elements and stirring new collapses elsewhere. Creation and destruction work hand in hand, cycling endlessly through the same material. The galaxy's brightness is almost beyond scale. Counting all wavelengths from radio murmurs to X-ray flare, its total energy rivals that of 1 trillion suns. Few galaxies in the known universe shine so intensely, yet the light is not evenly spread. Most of it emanates from the central nucleus and the youthful stars that burn nearby, while the older, redder stars make up the bulk of the mass, but little of the glow. Mass and light, energy and age, lie side by side but tell different stories. The environment around the galaxy is no gentle cradle. The intracluster gas presses inward, a hot ocean surrounding the cooler core. That pressure squeezes the galaxy's own atmosphere, while at the same time, energy from young stars and from the central black hole pushes outward. These two forces meet in a restless boundary layer, a thin and turbulent frontier where gas cools in some places, heats in others, and constantly changes direction. In X-ray images, this interface appears as a sharp, bright rim around the central glow, a luminous threshold between the galaxy's breadth and the cluster's deep silence beyond. To study this region is to glimpse how galaxies live and change. The Phoenix Cluster's central galaxy has taught astronomers that even the largest and most ancient systems can flare into sudden life when the conditions align. It shows that feedback from supermassive black holes, though fierce, does not always prevent cooling. That under the right balance of inflow and energy, the old can become new again. Without a steady stream of fresh gas from the cluster's vast reservoir, this rebirth would fade quickly. But as long as the flow continues, the furnace stays lit, and stars keep forming in defiance of expectation. The galaxy becomes, in this way, a laboratory of extremes, a natural experiment written in gravity and heat. Every observation refines our sense of how galaxies grow, how cooling and heating intertwine, how feedback falters, how creation finds its loopholes. It reminds us that cosmic order is not static, but dynamic, a dance of competing forces whose steps never quite repeat. Its future, though, is uncertain. If the cooling continues unchecked, the galaxy may double its stellar mass within a few 100 million years, burning through its supply of gas in a blaze of brief abundance. But the black hole at its heart may yet reassert control, releasing energy enough to warm the gas and still the storm. In that case, the galaxy would return to quiet, its fevered youth preserved only in the ages of its stars. Either path eruption or calm marks the same truth. Nothing in the cosmos stays fixed for long. What we see today is only a moment in a long evolution, a flash of imbalance before a new equilibrium settles in. The light that reaches us carries both the evidence of motion and the echo of change. It tells us that galaxies are not monuments, but organisms of matter and time breathing, shedding, remaking themselves. The central galaxy of the Phoenix Cluster, alive with birth and bound by gravity, stands as a portrait of that living process. It proves that even the oldest structures can be caught in the act of transformation, that the universe has never stopped experimenting with form. When that light finally arrives here, crossing 5 billion years of space, It comes as both revelation and reassurance. It tells us that creation is still ongoing, that the great machinery of the cosmos never rests, and that what we witness in the Phoenix cluster is not a relic, but a chapter still being written. Everything we see, the stars, the gas, the shadows of dark matter, belongs to a continuum of becoming. And somewhere, in the silence between those distant galaxies, the balance between cooling and heat tips again, and the universe begins another quiet act of renewal. Surrounding the galaxies of the Phoenix cluster, filling the dark spaces between them, is an invisible ocean, the intracluster medium. It is not water, but plasma, a vast, diffuse sea of gas heated to tens of millions of degrees by the slow violence of gravity. When the cluster formed, galaxies collided, gas clouds compressed, and gravitational energy was converted into heat. The result is this ocean of lightless fire, occupying the space between galaxies like a thin, glowing mist. It dominates the cluster's ordinary matter, outweighing all its stars and planets many times over. Though invisible to optical telescopes, the intracluster medium shines brightly in X-rays. Its presence is betrayed by a faint, high-energy radiance that washes across the void light, too energetic for human eyes, yet rich with information. In that glow, astronomers read the story of the cluster's assembly, the echoes of ancient collisions, the scars of mergers, the signature of stellar births and deaths that have enriched the gas with metals forged in the hearts of stars. At its heart, the temperature of this gas is staggering 30 million degrees or more, far hotter than the surface of any star. At such temperatures, atoms cannot remain whole. Electrons are stripped from nuclei, leaving a fully ionized plasma. The particles move at incredible speeds, colliding constantly, their motions releasing X-rays through a process called thermal Bremsstrahlung, literally, breaking radiation. Every impact sends out a pulse of light as charged particles slow in one another's electric fields. This quiet frenzy of motion fills the cluster with radiation, a constant exchange of heat and energy that slowly cools the gas over billions of years. The balance between heating and cooling defines the rhythm of the intracluster medium. Gravitational compression and the outflow of energy from galaxies warm it, while radiation steadily drains that energy away. The result is not chaos, but a fragile equilibrium, one that shifts across space and time. The gas is densest at the center, where the cluster's gravity is strongest, and grows more tenuous toward the edges, merging gradually with the thin intergalactic medium beyond. Near the center, the density may reach only a few particles in each cubic centimeter, less than any vacuum on Earth, yet enough to make the region glow. In the outskirts, the gas thins to almost nothing, its presence barely distinguishable from the cosmic background. This gradient mirrors the cluster's gravitational shape, a bowl of potential into which matter has settled, reaching a state called hydrostatic equilibrium, where the inward pull of gravity balances the outward pressure of heat. Astronomers can read this invisible landscape using X-ray imaging and spectroscopy. By measuring how the brightness and temperature change with distance from the center, they can map the cluster's total mass, including the hidden weight of dark matter. The chemistry of the gas reveals its history. Unlike the simple hydrogen and helium that filled the early universe, the intracluster medium of Phoenix carries heavier elements: oxygen, silicon, iron, and others forged long ago in stellar furnaces and flung outward by supernovae. These metals drift through the cluster, mixed by turbulence and the winds of galaxies, creating a record of everything that has lived and died within this cosmic city. Each atom of iron, each trace of oxygen is a memory, a sign that matter has already passed through the life cycle of stars, been reshaped by fusion, and returned to the wider cosmos. The abundance of these elements allows astronomers to estimate how much star formation has occurred within the cluster since its birth, how much gas has been recycled through stellar hearts. The intra-cluster medium is not just a plasma, it is an archive. But archives, like oceans, are never still. The hot gas flows and swirls, stirred by galaxies in motion and by the energy from the central black hole. As galaxies drift through it, they leave wakes trails of turbulence, like ships moving through fog. When clusters merge, shock waves ripple outward, heating and compressing the gas. Observations show sharp boundaries, known as cold fronts, where the temperature drops suddenly, and curved walls of compressed plasma, the aftermath of cosmic collisions still echoing through space. In high-resolution X-ray maps, these structures appear as folds and waves, each one a chapter in the cluster's continuing story. The Phoenix cluster's most remarkable feature lies within its center, a powerful cooling flow. Here, the gas is dense enough that it radiates energy rapidly, cooling on timescales of only a few 100 million years brief, compared to the age of the universe. As it cools, it sinks deeper into the gravitational well, becoming denser, cooling faster still. Left unchecked, this process would cause enormous amounts of gas to condense and fall into the central galaxy, igniting bursts of star formation and feeding the supermassive black hole. For decades, astronomers searched for such cooling flows across the universe. Theory predicted they should be common in massive clusters, yet most revealed little sign of the expected cold gas. The Phoenix cluster, however, breaks the pattern. It shows clear evidence of rapid cooling and the starburst it fuels, making it one of the best living examples of this process in action. In X-ray images, the cluster's core glows fiercely bright, compact, and concentrated. Spectroscopic studies show lines from cooler gas near the center, with temperatures dropping below 10 million degrees, evidence of matter in transition from hot plasma to cold molecular clouds. These clouds drift inward like slow rain, forming filaments that thread through the cluster, feeding the galaxy at the core. There, they collapse into stars at astonishing rates, hundreds of suns each year. The cooling and star formation seem to move in lockstep. As gas condenses, new stars ignite. Most of the cooled material is used almost immediately, transformed into stellar light. Yet the mystery remains. Why has the black hole's feedback not halted the process? In most clusters, jets and outflows from the central active nucleus provide enough energy to counteract cooling, maintaining equilibrium. In Phoenix, that balance has slipped. Jets and bubbles are visible, great cavities in the X-ray glow, where relativistic plasma has pushed aside the gas, but their energy appears insufficient to stem the flow. Perhaps the black hole's activity has dimmed temporarily, or perhaps the density of gas has risen too quickly to control. Whatever the cause, the cluster is caught in a rare imbalance, a fleeting moment when cooling wins. The intracluster medium does more than feed the heart of the cluster. It governs the fate of its galaxies. As each galaxy moves through the hot plasma, it experiences a kind of wind, called ram pressure, that pushes against it. If this wind is strong enough, it strips away the galaxy's own gas, removing the material needed to form new stars. Over time, spirals lose their arms, their blue light fades, and they settle into quiet ellipticals. This process, RAM pressure stripping, helps explain why galaxies in dense clusters tend to be older and redder than those in isolation. The environment itself shapes their evolution, sculpting their forms through invisible pressure. The ocean of plasma extends far beyond the bright core, stretching for millions of light years. In the outer regions, where the gas grows faint and cool, it merges with the filaments of the cosmic web, the highways of matter that connect clusters across the universe. Here, at the edge of Phoenix's domain, gas continues to flow inward, feeding the cluster's growth. The boundaries blur. What belongs to the cluster and what belongs to the universe beyond are not easily separated. Magnetic fields weave through this medium like hidden threads. Generated by the motion of charged particles and amplified by turbulence, they influence how heat and momentum are transported, how energy is shared between regions. These fields provide a subtle pressure of their own, supporting the gas against collapse, and they confine cosmic rays, high-energy particles, born from supernovae and from the jets of active galaxies. In radio light, astronomers can trace the spiraling paths of these electrons as they dance along magnetic lines, emitting the faint signature of synchrotron radiation. This interplay between magnetism, turbulence, gravity, and heat creates patterns more intricate than any single equation can describe. The intracluster medium becomes a living laboratory for plasma physics under extreme conditions. Its temperature, density, and motion cannot be reproduced on Earth. No machine can hold matter so hot, so thin, and so vast. Within it, processes like thermal conduction, viscosity, and turbulent mixing operate in exotic regimes, governed by the collective behavior of particles that rarely collide but constantly interact through electric and magnetic forces. By studying the Phoenix cluster, astronomers test the very foundations of physics. Its gas provides clues about how energy moves through plasmas, how magnetic fields evolve, and how turbulence transfers heat across cosmic distances. In that way, this cluster connects the smallest and largest scales, linking the microphysics of particles to the macroscopic flow of galaxies and clusters. The hot gas surrounding the galaxies serves both as record and participant. It remembers the past in its composition and structure, the enrichment from supernovae, the ripples from mergers, and it continues to shape the present by feeding galaxies and black holes. Every filament of X-ray light, every subtle gradient in temperature carries a trace of time. To read those traces is to reconstruct the cluster's biography, from its youth as a loose collection of galaxies to its current grandeur. Over billions of years, gravity gathered smaller groups, their collisions stirring the plasma and creating shock waves that still echo outward. These waves leave signatures, temperature jumps, arcs of brightness, asymmetries that betray the violence of the cluster's assembly. The Phoenix cluster is not static. It is a living monument to change, its hot medium still settling into balance after eons of motion. Through its study, humanity glimpses how order emerges from turbulence, how equilibrium is not peace but a continual conversation between forces. The Phoenix cluster teaches that even in the apparent stillness of space, the universe is alive with motion, gas cooling, stars forming, magnetic fields weaving, black holes breathing energy into the void. And across the gulf of 5 billion years, the light of that motion reaches us, soft, ancient, and full of meaning. It carries the memory of heat and the signature of change. In its glow, we see not only the Phoenix cluster, but the physics that governs all. matter the same laws that ignite stars and hold atoms together, playing out on scales beyond imagination. The cluster's intracluster medium, vast and radiant, stands as both mirror and map. It reflects the processes that built the cosmos and charts the pathways by which it continues to grow. To observe it is to listen to the deep murmur of creation still underway, to recognize that the universe, even now, is not finished with its making. At the center of the Phoenix Cluster's brightest galaxy, beneath a slow snowfall of antique starlight, sits a gravity so concentrated that space itself cups inward. Hidden in the densest knot of old red suns lies a supermassive black hole whose mass reaches into the billions of solar masses. You cannot see it. By definition, nothing that crosses its boundary returns with a message. Yet its presence is written everywhere around it, etched into the speed of orbiting gas, into the shape of surrounding light, into the heat and motion that ripple outward through the cluster's core. What seems like absence is, in practice, a conductor. The black hole draws in gas, stars, and dust, and in the act of drawing, it releases prodigious energy. Accretion matter spiraling inward turns gravity into light and motion. Radiant pressure, hot winds, and narrow jets pour back into the environment the very energy that infall liberates. In this way, the black hole becomes both restraint and engine, a quiet arbiter of how the core lives. It consumes, yet it also keeps the cluster from drowning in its own cooling, preventing a flood of gas that the galaxy could never process in time. This central darkness is among the most massive of its kind known. Its biography is a long accumulation written on cosmic timescales. In the young universe, seeds formed from the deaths of the earliest massive stars, brief lives collapsing into compact remnants, or, more rarely, from the direct implosion of titanic gas clouds that bypassed the star-making step altogether. Those initial seeds, only tens or hundreds of solar masses, were small beginnings. Growth came through two channels repeated again and again: accretion, the slow eating of gas, and mergers, the conjoining of black holes when their host galaxies combined. Each merger made a heavier remnant. Each inflow fed the central mole. Each episode of feeding released light and motion that, paradoxically, regulated the next meal. How heavy is such a darkness? Astronomers listen to motion for the answer. Near the core, gas and stars whirl at hundreds of kilometers per second. When their light is split into spectra, the lines emerge broadened and shifted. Speed and gravity do that. With careful models that account for geometry, projection, and every visible mass that tugs nearby, the central black hole's weight is inferred to be several billion suns. The exact figure carries uncertainty. Dust hides, turbulence confuses, and orbits rarely move in clean circles, but the scale is unmistakable. In the galaxy's heart, this single object is the dominant source of gravity. Matter does not fall in like rain. Angular momentum, the preference to spin, forces in falling gas into a disk, a thin whirlpool that glows. Friction between neighboring rings, magnetic stresses that tug and twist, and shocks where streams meet translate orbital energy into heat. Close to the event horizon, the temperatures climb to millions of degrees. Iron atoms there betray their environment. Their spectral fingerprints smear and skew, altered by relativistic speeds and the curvature of space-time itself. From infrared to X-rays, the disk shines, presenting the paradox of black holes, darkness that announces itself through the brightness it induces in everything just outside its edge. The rate of feeding sets the tone. In the Phoenix core, the accretion is not the raging, blinding torrent that marks the brightest quasars, yet it is anything but faint. The active nucleus outshines the starlight of the entire galaxy, the way a steady flame can eclipse a field of embers. That energy couples to the surrounding medium as heat, as radiation pressure that pushes on dust and gas, and as outflows. Most striking among these are jets, pencil-thin beams of plasma accelerated to near light speed, guided by magnetic fields that anchor in the disk and likely thread the black hole itself. There is an elegant mismatch between cause and effect. The engine, an event horizon that would fit within the orbit of Neptune, drives structures that stretch for hundreds of thousands of light-years. That is the signature of jet physics in curved space-time. Magnetohydrodynamics, the marriage of fluid motion, electricity, and magnetism, predicts that rotational energy can be tapped and turned into directed motion. The faster the spin and the stronger the magnetic fields, the more efficiently the engine can throw matter outward. Under the right conditions, a fraction of the rest mass energy of what falls in is redirected into the kinetic energy of what is launched out. Tiny scales pull the strings of vast ones. Those jets do work on their surroundings. As they pierce the galaxy and enter the cluster's hot atmosphere, they shove the intra-cluster medium aside, inflating bubble-like cavities. In deep X-ray images, the bubbles appear as dim pockets. In radio images, they glow with synchrotron emission from electrons spiraling along magnetic field lines. The cavities rise through the stratified gas like hot balloons, mixing, stirring, and heating the medium as they go. Their edges can be sharp or frayed, depending on how turbulence and magnetism delimit the boundary. From their sizes, pressures, and buoyant speeds, astronomers estimate the mechanical power of the central engine not only now, but integrated over the last many millions of years. That mechanical power feeds back into the cooling that otherwise would cascade unchecked. Feedback is the term for this conversation between the tiny engine and the enormous environment. In many clusters, that conversation lands on a working compromise. Heating nearly balances radiative loss, cooling flows are slowed, and star formation in the core dwindles to a whisper. Phoenix refuses the usual ending. Here, for a span of time, cooling has outpaced heating. Dense gas in the core has radiated away its energy fast enough to condense into filaments and clouds, which then collapsed into stars. The galaxy's ancient red light is stitched with new blue embroidery. Jets and bubbles are present, visible, and energetic, but not quite energetic enough to shut the valve. The system appears to be caught in a transient tilt, where gravity's pull on cool gas gets ahead. Radio maps trace the aftermath. In those wavelengths, the cluster's heart looks like calligraphy, thin strokes marking where the jets run and where they once ran. The cavities remember former outbursts. Some are still fed. Others drift silently, their plasma aging, their electrons cooling, their glow fading but not gone. The X-ray image overlays another language, ripples, rims, and sharp edges that record pressure waves, cold fronts, and shocks. Together, the languages of radio and X-ray reveal a history of pulses, the nucleus breathing, exhaling energy in episodes, then resting between them. From these pale fossils of motion, astronomers reconstruct a duty cycle. Feeding does not proceed continuously. It is episodic, like rainstorms, separated by clearings. Fuel arrives in clumps and threads, some stripped from passing galaxies by ram pressure, some distilled from the cluster's own cooling atmosphere, some delivered by messy mergers that tilt orbits and confuse gas into new pathways. When supply is healthy, the nucleus brightens and jets strengthen. As supply wanes, the engine idles, the bubbles shrink, and the core has a chance to cool again. A feedback thermostat runs not perfectly, not instantly, but on average, over time tuning heating to match cooling. Phoenix shows what happens when that thermostat drifts. The black hole and the galaxy that homes it grow together. Across the nearby universe, there is a tight correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge. That relation implies co-evolution. The galaxy provides gas and occasional companion black holes through mergers. The black hole, by returning energy to the gas, limits how fast the galaxy can form new stars. Press too hard with outflows, and the gas warms and thins. Star formation falters. Fail to press hard enough and the gas drops out of the hot phase, raining into the core and igniting a burst. Somewhere between those extremes lies a shifting, living balance. Closer to the horizon, the physics becomes intimate. For a black hole of several billion solar masses, the event horizon's radius is on the order of 10 billion kilometers, a region that would fit inside the orbit of Saturn. A small realm compared to galactic scales, but unimaginably dense. From 5 billion light-years away, that scale is vanishingly small. No present telescope can resolve it. We do not see the horizon, we see its consequences. Gas that skims the last stable orbit smears its spectral lines. Light emitted from close in is stretched by gravitational redshift as it climbs out of the deep well. Space itself is twisted by rotation frame, dragging so that even light feels a slight rotational tug. The innermost part of the disk runs with relativistic speeds. Time slows there, clocks tick differently, and straight paths curve of necessity. Spin is the hidden dial that tunes the engine's song. Accretion that carries angular momentum tends to spin a black hole up over time, while mergers can add or subtract, depending on alignment. A rapidly spinning black hole pulls the innermost stable orbit inward, allowing matter to dive deeper before crossing the horizon. Deeper dives mean more energy that can, in principle, be tapped. Magnetic fields that thread the disk and the black hole itself can connect rotation to outflow, extracting energy to power jets. Observational hints, broad iron lines, jet morphologies, and the sheer mechanical output implied by the cavities support the idea that Phoenix's central engine is spinning quickly, though the numbers are necessarily indirect. Relativity dominates this neighborhood. Light that passes close can loop partway around before escaping, creating distorted, energy-shifted images of the inner disk. Photons that escape carry imprinted on their wavelengths the story of the gravity they endured. These effects have been photographed directly only for nearby giants, where arrays of radio dishes combined into the Event Horizon Telescope have captured horizon-scale shadows. Phoenix lies far beyond such resolution, but the same equations apply. The same physics shapes its hidden edge. We read it not in silhouette, but in implications' broadened lines, high-energy tails, patterns of variability. All power is conditional upon supply. As long as filaments continue to deliver cold gas into the core, as long as stripped interlopers shed their atmospheres into the cluster's wind, as long as the intracluster medium condenses at the center, the black hole will eat. And in eating, light the core and breathe out jets. If supply weakens because feedback finally warms the reservoir, because geometry shifts and magnetic fields redirect, inflow the nucleus will dim. The gravity will remain, a quiet tyrant fixing the orbits of stars. The marks of past brightness will remain, as bubbles and ripples fossilized in the hot gas. Activity comes and goes. Influence persists. This is the most striking aspect of the system. It ties together scales that usually live far apart. Viscosity, in a disk only light hours across, sets the terms for winds that shape gas across tens of kiloparsecs. The twist of a magnetic rope near the horizon adjusts the temperature profile of a plasma spread through a galactic core. The microphysics of particles and fields, collisions rare, collective effects dominant, reaches outward to sculpt the macrostructure of an entire cluster. The unity is not metaphor. It is the way the universe is patterned. The same laws, repeating across context and size. Origin invites its twin, the question of limit. How many mergers did it take to build this mass? How often did the Phoenix core blaze like a bright quasar? And how long did those phases last? What reigns in growth before it runs away? Likely, the ceiling is written in the flow of supply and the success of feedback. Pour in gas faster than the engine can heat, and the core floods with cold material. Star formation surges, and the black hole's meal swells. Turn the jets and winds too strong, and the pantry empties. The gas thins, and the engine starves. The balance rocks on a fulcrum that moves with time, a thermostat that overshoots and corrects, never perfectly, always adjusting. It helps to picture the horizon not as a surface, but as a rule. The event horizon is a boundary of paths, a region from which every future direction leads inward. Matter crossing it does not scream. There is no edge to touch. Energy and angular momentum are shed outside, in the disk and the jets, where we can still read them in light. Inside, the story closes. What infalls adds mass, adds spin, and deepens the well without a word. We are left with what we can observe. The last acts written in radiation, the accounting done in spectra, the totals inferred in the shapes of gas and the shifting of stars. And the future? If the cooling flow continues at its present pace, the central galaxy could double its stellar mass in a few 100 million years. The blue of newborn stars would slowly give way to warmer hues as those populations age. Fresh filaments would arrive and ignite another round. The engine would feed and return energy in cycles. If, instead, feedback catches up, if jets strengthen, if bubbles couple more effectively to the core, then star formation will diminish. The gas will remain hot, and the nucleus will settle into comparative quiet. Neither endpoint is permanent. The system will likely alternate, a long, slow breathing of creation and restraint. The archive of those breaths will remain in the X-ray rims and radio shells, in the ages of stars that testify to bursts long past. All of this understanding rests on light, patiently gathered. We listen in radio to trace the jets and the magnetic filaments, in infrared to see dust warmed by newborn stars, in optical to weigh stellar motions and map ionized gas, in X-rays to read the heat and pressure of the plasma. Each band is a sense. Together, they give depth, like night vision sharpened by practice. With those senses combined, we reconstruct a place we will never visit in person. A galaxy whose heart is smaller than a planetary system, yet louder than 1,000 normal galaxies. A fountainhead where gravity turns inward and illumination turns outward. Stand back, and the layers align. Dark matter provides the scaffold. The intracluster medium fills the scaffold with hot, enriched plasma. The central galaxy gathers what falls. Its supermassive black hole sets the pace for what can cool and what must remain warm. Turbulence translates small motions into heat. Magnetic fields reroute flows. Supernovae surround the core with heavier elements. Then the black hole stirs the pot again. Everything is coupled. Everything shares. And so the Phoenix cluster's nucleus becomes more than a curiosity. It is a teacher of proportion. It shows how a thing the size of a solar system can impose order on a region hundreds of thousands of light-years across. It shows how a sequence of events, seed, growth, merger, ignition, feedback repeats across epochs until a monument forms that is less a statue than a living process. It shows that balance is not stillness, but the continuous exchange of energy across scales. A conversation that sounds almost like a long, low note. Imagine that note. Imagine the core turning in the dark. The outer stars keep their stately distances. The young blue knots will, in time, fade to white and then to amber, joining the elder population whose light is a slow glow rather than a flame. Filaments of cold gas drift inward like pale threads on a black river, breaking, knotting, falling. Deep inside, magnetic fields tighten like the strings of a harp. The accretion disk hums. The jets write thin script across the X-ray sky. Shock fronts curl around the cavities they have carved, whisper thin walls of pressure traveling outward. Ripples meet ripples and interfere. A quiet storm in very slow motion. In that long music, destruction and creation resolve into a single chord. Matter falls and is unmade as matter. Energy rises and remakes the surroundings. The black hole grows heavier and spins. The galaxy reworks its gas into stars. The cluster adjusts its temperature one bubble at a time. Nothing settles forever. The universe likes to keep writing. And here, at this one bright center, the writing is easy to hear. A reminder that even where darkness holds, the work of making and unmaking goes on, measured not in minutes or ages, but in the steady patience of gravity and light. The cluster's story keeps unfolding in the same patient hand, and now the script brightens. Star birth surges through the core. In the central galaxy of Phoenix, the rate of creation rises to a steady hum, more than 700 suns worth of new stars each year. That pace surpasses many entire galaxies and outstrips any cooling flow system astronomers had seen before. A quiescent elliptical becomes, for a time, a forge. The old red glow is threaded with blue fire, rivaling the wildest starbursts of the early universe, while standing here, improbably, in a mature cluster. Such intensity was not the usual expectation for seasoned systems. It bends the curve of habit, reminding us that even where gravity seems to have settled its accounts, a small imbalance can gather into transformation when conditions align and time is allowed to work. Every star begins as a hush inside cold, dense gas. Gravity leans in. Turbulence, magnetic pressure, and thermal motion lean back. Where gravity gathers the upper hand, a cloud collapses and fractures into clumps. Each one, a cradle with its own slow heartbeat. In Phoenix's heart, the intracluster medium keeps sending down fresh threads of cooled material. Those threads pool into vast molecular reservoirs, and the high pressure of the cluster core helps the clouds hold together long enough for gravity to finish its quiet work. The pattern on the sky is not smooth. In infrared and sub-millimeter light, where warm dust betrays the presence of young stars, the core blooms with speckled brightness filaments and knots, laced across the inner few 100,000 light-years. These bright patches map the lanes where gas flows inward. Some clouds carry millions of solar masses. Within each, thousands of suns are born at once. Star formation follows density, so the new light clusters along the paths carved by the cooling flow, rather than spreading evenly. A tapestry woven by pressure, gravity, and time. The newborn population spans many masses, but the loudest voices are the giants, stars, tens, or even hundreds of times heavier than the Sunday. They pour ultraviolet light into their surroundings, peeling electrons from atoms and turning the gas into luminous H2 regions. Winds from these massive stars push outward at thousands of kilometers per second, carving cavities, squeezing some pockets of gas into new collapses and dispersing others before they can settle. A few million years later, less than an eyelash in cosmic time, the brightest giants exhaust their fuel and end as supernovae, their shock fronts rolling through the clouds like thunder, stirring the medium with heat, metals, and momentum. How fast is fast in numbers you can trust? Astronomers weigh the pace 3 ways, each with different strengths and blind spots. First, the total infrared luminosity tallies the warmth of dust grains heated by the hidden glow of young stars. The brighter the far infrared, the more intense the nursery behind it. Second, the strength of hydrogen recombination lines photons freed when ionized gas reclaims its electrons, betrays how many massive stars are bathing the clouds in ultraviolet light. Third, the ultraviolet continuum measures the raw brilliance of young stellar surfaces before dust can swallow it. In Phoenix, all 3 methods converge on the same conclusion: a star formation rate exceeding 700 solar masses per year. Agreement across wavelengths turns a startling claim into a measured fact. Such a furnace requires fuel an ocean of cold, dense gas. Molecular line observations, especially from carbon monoxide that traces H2, reveal a reservoir exceeding 10 billion solar masses in the central galaxy. This material began as part of the hot intra-cluster medium and then, through the steady radiative shedding of energy, condensed into clouds only a few tens of degrees above absolute zero. Cooling is fastest where density is greatest, so the effect compounds. Denser gas cools more quickly, which makes it denser still, which quickens the fall, a feedback of quietness that gravity favors. Cooling, infall, starbirth, the chain links directly. X-ray diagnostics estimate how much mass the core gas is losing to radiation each year. The tally aligns closely with the rate of star formation inferred at other wavelengths. That concordance means the cooled gas is not merely hoarding in some hidden reservoir, it is actively turning into stars. The Phoenix core thus stands as a rare, vivid example of the classic cooling flow, once predicted for many clusters, but seldom caught in the act. Star formation writes its own feedback into the scene. Every supernova releases, in a few heartbeats, energy comparable to the sun's entire lifetime output. When many detonate in crowded neighborhoods, their blast waves overlap, driving outflows that blow gas from the densest clumps and heat the surroundings. Filaments of ionized gas expand like soap bubbles. Some burst, venting material into the wider medium. Some stall and cool, collapsing again later. This self-limiting behavior keeps the frenzy from burning through the supply all at once, giving the system room to breathe between surges. The burst will leave signatures that linger for ages. Massive stars enrich the gas with carbon, oxygen, silicon, and iron. Their ashes seed the next generation of clouds, tilting chemistry toward complexity. Lower mass stars, formed in the same epoch, will keep glowing for billions of years, eventually swelling into red giants and settling as white dwarfs. Long after the current blaze fades, the galaxy will wear its history in the ages and metallicities of its stars, a fossil record, written in spectra and preserved in the color of light. Context sharpens meaning. In the early universe, when galaxies were young and gas was plentiful, star formation rates of hundreds or thousands of solar masses per year were commonplace. Mergers were frequent, and inflows along cosmic filaments were strong. Starbursts built massive galaxies in brief, intense episodes. Today's cosmos is calmer. Such extremes are rarer, usually sparked by major mergers or by unusual gas supplies. Phoenix looks modern but behaves ancient, echoing early epoch physics inside a present-day frame. Scale adds its own surprise. Many starburst galaxies concentrate their activity into compact nuclear regions, a few hundred or a few thousand light-years wide. In Phoenix, star formation is extended across hundreds of thousands of light-years. It fills the inner galaxy and laces into the surrounding filaments, a broad canvas painted by a large-scale cooling flow rather than a single funnel to the nucleus. The result is a spatial tapestry, where young blue populations mingle with elder red stars, where dust lanes thread between bright knots, and where glowing arcs mark the footprints of expanding shells and shocks. Theory bends to observation and then straightens again. Models of cooling flows and feedback must explain why Phoenix blazes while most clusters hold their cores in check. Possibilities multiply and then narrow. Perhaps the central black hole's activity runs in a duty cycle, and we are catching it during a lull. Perhaps a recent merger spiked the core density, overwhelming the usual heating. Perhaps magnetic geometry has, for now, made the coupling between jet energy and core gas less efficient, letting more of the cool material slip inward before being reheated. Each scenario keeps the same physics, but shifts the timing and the leverage. The Phoenix core also lets astronomers probe the initial mass function, the distribution of masses with which stars are born. In most places we've looked, that distribution appears nearly universal. Many low-mass stars, fewer intermediate, and very few high-mass giants. In extreme environments, theory allows the possibility of a top-heavy tilt that favors massive stars. If Phoenix is such a place, we would expect stronger ultraviolet and supernova indicators per unit star formation, different chemical yields written in the gas, and a stellar population whose subsequent evolution brightens certain wavelengths for longer than usual. Observations there become not just a census of light, but a test of whether the recipe of star birth is truly universal or sensitive to pressure, turbulence, and radiation field. None of this lasts forever. The starburst is a phase spectacular, brief by cosmic standards, and bound by supply. If cooling continues unabated, the central galaxy could double its stellar mass within a few 100 million years, its blue sheen slowly warming as populations age and the burst eases. If, instead, feedback from the black hole and the combined winds of young stars finally outrun the inflow-strengthening jets, inflating larger bubbles, stirring turbulence that mixes heat into the core, then the fuel will thin and the pace will slow. Either route is consistent with the same laws. The question is one of timing and balance. Seen from here, all of this is memory. The light that shows us Phoenix's frenzy left more than 5 billion years ago. The most massive stars from that epoch have already exploded. Their heavy elements are now folded into new clouds or spread into the cluster's wider medium. The smaller, steadier stars are still shining, age creeping into their colors. The galaxy may have quieted, or it may have flared again. We cannot yet tell. What we hold is a snapshot of a furnace mid-roar, a page from a book still being written. Even the way the star formation spreads across space speaks to the large-scale engine that feeds it. The filaments are not random. They trace lines of force and flows set by gravity, pressure, and magnetism. Cold gas prefers paths where magnetic fields guide and turbulence thins. Where filaments cross or stall, clusters of stars flare into being. Where outflows from supernovae or the active nucleus plow into inward-moving streams, shock-compressed ridges light up briefly and then fade as the geometry shifts and the gas reroutes. Measurements reach deeper than pictures. Spectroscopy, with its quiet array of lines, passes the temperatures, densities, and motions in each bright knot. Ratios of oxygen to hydrogen, of nitrogen to sulfur, carry the imprint of how many generations of stars have lived and died. Line widths tell of turbulence. Line shifts reveal bulk motion along the line of sight. In the far infrared, fine structure lines measure cooling directly. In the sub-millimeter, rotational transitions of CO map the cold reservoir. In the millimeter and radio, dense gas tracers like HCN and HCO mice take the census of the very cores where stars are about to be born. Cross-checked against X-ray measurements of the hot atmosphere, the data draw a closed loop. What cools, condenses. What condenses forms stars. What forms stars returns heat and metals. What is heated resists collapse until it, too, can cool again. Comparisons across cosmic time sharpen the lesson. High redshift starbursts often arise from galactic collisions, where tidal forces drive gas inward and compress it. Phoenix achieves similar intensities through a different route, the slow rain of a cooling atmosphere, confined by an enormous gravitational well. The resemblance of outcome with difference of cause hints at a deeper commonality. Whenever cold gas piles up faster than feedback can disperse it, stars ignite in torrents. The universe seems to care more about the ratio of supply to resistance than about the specific route that sets it. And all the while, the central black hole plays metronome. Its outflows carve cavities. Its radiation warms dust. Its variability sends ripples through the rates at which clouds can collapse. Sometimes the metronome runs ahead of the beat. Sometimes it lags. Phoenix is the sound of the music when the tempo leans toward creation. There is tenderness in the violence of it. Picture the inner galaxy in dim light. Lanes of dust like strokes of charcoal across the glow. Threads of cold gas gliding inward, pale and quiet. Pockets where ultraviolet light halos the newest clusters. Arcs where wind-shocked shells expand, thin and break. Remote cavities in the X-ray sea, their edges soft as breath. Everywhere, feedback nudges never quite canceling the fall, never quite yielding full control. The system, like a chest rising and falling in sleep, keeps time with a cycle of cooling and heat. What Phoenix shows, set against the wide calm of the cluster, is that creation can surge even in places we thought were finished. A galaxy long considered red and dead can, given fuel and a brief alignment of forces, bloom like a sudden spring. The laws have not changed. The balance has. The numbers circle back to feeling. 700 solar masses per year is not just a statistic, but an image of thousands of new suns each century, millions each million years, each with possible worlds, each with futures we will never see. The metals forged in their cores will drift outward, tinting the next clouds, brightening the next generation. The burst, brief as it is, becomes part of a longer weave, the ongoing enrichment of the cluster, the slow accumulation of light. Scale your view once more and let the picture hold. The cluster hums, the nucleus breathes, filaments dim and brighten, the blue disperses into gold. Somewhere, beyond our reach, the balance tilts again, cooling gathers, heating answers, and the universe turns another page with the same patient hand, the same soft insistence that nothing is finished as long as there is gas to fall and gravity to catch it, as long as light can be made from the hush of cold. From that bright center, the script writes itself in lines so thin they look like intention made visible. Twin beams of relativistic plasma slip outward from the accretion disk, like needles through fabric, nearly at light speed, narrow where they begin, and then slowly loosening as they meet resistance. They pass through the hot atmosphere of the cluster and carve out cavities that appear in X-ray images like thumbprints pressed into glowing glass. What begins smaller than a solar system traces structures hundreds of thousands of light years long, a reminder that a compact engine can move a world of air. The power behind those beams is the same steady conversion that turns falling into light. Matter spirals inward. Some fraction of its gravitational energy is redirected into kinetic form, accelerated particles braided with magnetic fields. The efficiency of this engine remains startling, as though nature found a way to pour mass into motion with almost no spillage. Close to the black hole, the disk rotates differentially, inner rings overtaking outer ones, and the shear twists magnetic field lines into taut ropes. When the geometry and strength are right, those ropes fling plasma along the spin axis, guiding it into collimated jets that depart with purpose and speed. The details are still an open page in the handbook of physics: how the fields anchor, how the black hole's spin injects energy, how the flow stays narrow, so near the start. But the broad pattern repeats from stellar mass black holes in our own galaxy to the giants in clusters like Phoenix. Scale changes, the method holds. As the beams travel outward, the environment answers. They push on the intracluster medium, doing work the way a hand does work on water, scooping and swelling. Bubbles of relativistic plasma inflate where the jets linger, little by little evacuating regions that show up as dimples in the X-ray glow. The pressure inside the cavities balances the weight of the gas around them. The edges become bright rims where shock waves heat and compress the plasma. Estimating the energy is a matter of measuring sizes, pressures, and buoyant rise times. The numbers fall into place. Mechanical powers that would dwarf the light of whole galaxies, maintained for millions of years at a stretch. Sustained, such power can offset cooling in the core, halting what would otherwise be a runaway condensation. The bubbles do not hang in place. Like lanterns released into a river, they rise, dragging tendrils of gas behind them. Their ascent stirs turbulence. Their wakes mix hot and cool material. Their motion redistributes metals forged in stars and dust born of them. Along their leading edges, where motion meets resistance, shocks curl and move outward, subtle ripples inflating the atmosphere with heat. Behind them, the displaced gas flows back, setting up circulations that ferry energy and momentum through the core. These currents are too slow to watch in real time, but their fingerprints linger. The temperature map remembers where a shock passed. The density map retains the arc of a cavity. The distribution of metals shows where mixing has been generous and where it has left shadows. Look at the radio sky, and the script turns into calligraphy. Synchrotron emission outlines where electrons, whipped to near-light speeds, spiral through magnetic fields. The jets become luminous threads, The plasma-filled bubbles become soft radio lobes. Bright knots mark impacts where a jet encounters denser gas, shocks it, and briefly flares. The spectrum of the radio glow, steeper at higher frequencies, tells of aging electrons losing energy. Flatter patches betray ongoing acceleration. Following the colors across frequencies is like reading the time since the last push, counting the years and how the glow has dimmed. The jets do not run forever. They operate in episodes. A surge of activity, an interval of quiet, another surge. Each episode inflates a new set of cavities that rise and fade by degrees, nesting one within another like growth rings in wood. The Phoenix core bears these rings multiple generations of bubbles, some crisp and new, some ghostly and thin. Stack them by size and distance from the center, and you reconstruct a duty cycle. How often the engine switched on, how long it pushed, how much it rested. The cadence matters, because the core's heat budget depends not just on total energy, but on timing. Heat delivered too rarely allows the gas to cool and condense between pulses. Heat delivered too often overstirs the medium, thinning it and quenching star formation before fuel can gather. Phoenix sits where timing, power, and supply have drifted into a narrow corridor, where cooling wins more than expected, but not yet decisively. Feedback reaches beyond the core's immediate glow. A hotter, pressurized atmosphere is less willing to surrender its energy, and gas that would otherwise settle onto orbiting galaxies remains aloof. Spirals falling into the cluster feel both ram pressure from the wind of the hot medium and the gentle rationing of fuel from the core's heat. Gas is stripped from disks, star formation slows, and galaxies redden into quieter shapes. On average, across long spans, jets help set the pace at which the cluster converts gas into stars. They are regulators rather than executioners, careful with their influence, persuasive enough to keep the ledger near balance, but not always strong enough to stop every local rush. In Phoenix, the ledger is tilted toward cooling despite active jets and visible cavities. A temporary rise in core density, a lull in jet power, or a mismatch in how the jet energy couples to the gas could each explain the imbalance. A recent merger might have funneled fresh material into the center. A change in magnetic topology might be letting more energy escape along paths that don't warm the densest regions. Turbulence may be distributing heat broadly, when what's needed is to seed warmth into the very places where cooling accelerates. The system is complex and honest about its complexity. It resists single cause stories. Momentum rides the beams as surely as energy does. Jets push forward, but as they do, they impart subtle twists and sideways drifts to the medium they cross. The resulting velocity field is not simply in and out, it swirls. Spectroscopic maps of emission lines, shifted by motion along our line of sight, reveal eddies and shears that match the footprints of recent episodes. Turbulence that begins as a narrow channel widens into a field, helping to distribute the jet's energy beyond the exact path of the beams. Heating, therefore, is not a thin needle of influence, but a fan, spread by chaos into volume. The relativistic electrons that outline the jets in radio do double duty as calorimeters of the universe itself. Wherever they pass through the ever-present bath of the cosmic microwave background, they scatter its low-energy photons up to X-ray and gamma-ray energies in inverse Compton exchange. Compare that high-energy signal to the synchrotron radio glow, and you can infer how the energy is split between particles and fields. How much pressure is magnetic, and how much is kinetic. Fill in those numbers, and the bubble's ledger balances more tightly. The work done against the surrounding gas, the energy stored, the energy leaking away, All of this jets, bubbles, shocks, wakes, ties the black hole's local mechanics to the cluster's global weather. The smallest scales set the tone. The largest scales take it up and modulate it. A rotation rate near an event horizon can change the temperature profile 100,000 light-years away. A change in the field geometry measured in light minutes can redirect energy that shows up 1,000,000 years later as a cavity, a galaxy wide. The unity is not a metaphor for interconnectedness. It is the mathematical fact of coupled equations playing out in real space. The future of the beams remains conditional on fuel. As long as cold gas continues to thread into the central parsecs, the accretion will pulse, and the jets will reappear in cycles, sometimes narrow and forceful, sometimes softer, sometimes bent by crosswinds in the plasma sea. If the supply is starved by feedback that finally catches up, by geometry that diverts inflow, by turbulence that shreds filaments before they can land, the engine will idle. The old cavities will continue to rise and fade. The ripples will flatten into gradients. The core will cool again on its own patient schedule. The story breathes. To see the whole choreography clearly, you need more than one sense. Each wavelength is a different fingertip on the same pulse. Radio light sketches the relativistic plasma, mapping where particles and magnetic fields have agreed to dance. Infrared light adds the warmth of dust grains heated by young stars, counting the hidden nurseries that optical light cannot pierce. Optical images show you the galaxies themselves, the knots and filaments of ionized gas around newborn clusters, the arcs of lensed background galaxies whose light bends around the cluster's mass. Ultraviolet carries the raw glow of the hottest young stars, a direct testimony that birth is recent and ongoing. X-rays reveal the hot atmosphere in all its layered structure. The cool core, the hotter outskirts, the cavities, the shocks, the fronts where temperature jumps and pressure smooths. Seen in radio, Phoenix grows filaments and lobes that trace the past routes of jets. Observe at multiple radio frequencies, and the spectrum tilts steeper where electrons have aged, flatter where acceleration is fresh. The steepness becomes a clock. The brightness becomes a measure of density and field strength. The map that results is a ghostly architecture of pressure and memory. Sometimes diffuse radio emission appears far from the core, halos and relics that testify to shocks and turbulence stirred up by mergers on larger scales, independent of the central engine. Even those broad features can help, scattering energy and seeding magnetic fields that later shape how jets propagate. In the infrared, space telescopes have taken the measure of dust warmed by young stars in the Phoenix core. The total infrared luminosity translates cleanly to a star formation rate when calibrated by local systems, and the number remains emphatically large, hundreds of solar masses per year. Spectral features add texture, vibrational modes of molecules, broad dust bands, fine structure lines that measure density and radiation fields. Each line becomes a gauge. Each ratio becomes a pressure readout or a thermometer. Each continuum slope becomes a tally of starlight absorbed and re-emitted. Optical images bring the scene into familiar focus. Thousands of galaxies filling the frame, their colors telling you which are young and gas-rich, which are old and quiet. Spectroscopy ties them into a three-dimensional cluster, measuring redshifts to confirm which objects share the Phoenix cradle and which are projected foregrounds or backgrounds. Around the central galaxy, strings and curls of emission mark where ionized gas hugs filaments or drapes along dust lanes. The morphologies of satellites, spiral arms, shredded or intact, disks tilted, bars stretched record how the cluster's gravity and wind have worked them over time. Ultraviolet observations take you directly into the heart of youth. The most massive stars shine strongest at those wavelengths, and when space telescopes gather that light, they confirm what the infrared implied. There is a young, hot population burning now, or rather, burning then and still visible now, that has no business being so intense in a galaxy that looks ancient in red light alone. The ultraviolet photons also turn surrounding gas into ions, whose recombination lines later show up in the optical. Cross-compare those bands, and the geometry of emission and absorption tightens into a map of where dust hides, where gas flows, where stars step out from their cradles. X-rays carry the weight of the atmosphere itself. Chandra and XMM Newton have mapped temperatures, densities, and pressures with exquisite delicacy, tracing the cool core, the gradients outward, the cavities that read like missing pieces in an otherwise continuous glow. Spectroscopy in X-rays reveals the fingerprints of highly ionized metals: iron, silicon, sulfur, each one a relic of stellar death spread into the plasma. Those lines fix the chemical composition. The composition fixes the cooling rate. The cooling rate, matched against the power inferred for the jets, closes the loop on whether feedback is holding the line or falling behind. Subtle changes in the X-ray point source at the center betray changes in the accretion rate, hinting that the engine's appetite varies on humanly tractable timescales of years to decades. The energy ledger for the entire cluster adds the pieces and asks whether they balance. Radiative losses in X-rays must be paid for by gravitational energy released as matter falls inward, by jet power that thumps heat into the core, by turbulence that turns bulk motion into warmth, and by supernovae that salt the medium with both metals and momentum. In Phoenix, the totals are large on both sides. A core cooling flow that would be decisive in most environments. Jets strong enough to etch bubbles, but, for now, not enough to erase the flow. Star formation that writes feedback of its own. Models that match these observed budgets earn the right to call themselves explanations. Those that miss a term must be amended or set aside. Some elements of the system would be invisible without the right eyes. The coldest star-forming gas is all but mute in optical light. It speaks instead in millimeter and sub-millimeter bands, where carbon monoxide and other molecules rotate and radiate. ALMA has heard those lines in Phoenix, mapping the distribution and speed of the molecular filaments as they arc toward the core and gather into knots, where stars will ignite. The data reveal not just where the gas is, but how it moves, whether it falls in clean, orbits and stalls, or is yanked and shredded by winds and shocks. Measurements of line widths and shifts draw the mass budget of the fuel directly, something no other band can do with such candor. The jet's plasma, in turn, announces itself in X-rays through inverse Compton scattering, a glow that radio alone would never reveal. Combining that with the radio map pulls back the curtain on the partition of energy. How much resides in particles? How much in fields? How much in heat? Synergy is not a flourish here. It is the only way the whole picture comes into view. A single band gives you a single story. Together, the stories self-correct and cohere. The instruments differ and demand care. Radio arrays synthesize images from many small dishes. X-ray telescopes count scarce photons one by one. Infrared detectors keep to cold to see warm. Optical spectrographs slice light into rainbows and then stack the rainbows into maps, aligning their images and cross-calibrating their scales is deliberate work, but the reward is proportionate. Misalign a cavity by a few arc seconds and you might miss the radio lobe that fills it. Miscalibrate a spectrum and you might misstate a temperature by millions of degrees. The craft of coordination is part of the science. With each advance in technology, the portrait sharpens. New X-ray missions promise to map turbulence directly by measuring tiny shifts in emission lines, a weather report for the plasma sea. Next-generation radio arrays will trace magnetic fields through polarized emission with a clarity that could reveal the very braids that hold jets tight near their launch. Infrared observatories will weigh dust masses with unprecedented sensitivity and track the chemistry of star-forming regions, cloud by cloud. High-energy telescopes will catch more of the inverse Compton glow and better constrain the content of the bubbles. Millimeter arrays will draw the filaments like threads on black silk, stitch by stitch. Across it all, the philosophy remains simple. The universe is speaking in many dialects of light, and understanding requires listening to them together. Phoenix becomes less a mystery and more a narrative, a system where gravity, heat, magnetism, and motion share the work of making and unmaking structure. The jets are not adornments, they are arteries. The bubbles are not gaps, they are footprints. The filaments are not accidents, they are roots. And the glow, thin but persistent across the spectrum, is the archive where everything that happened has left a trace. Step back one last time and hold the full multi-wavelength image in mind. Radio maps sketch the flowing ink of the jets and lobes. Infrared surveys lay down the warm hush of dust, counting hidden youth. Optical views populate the frame with galaxies, their shapes and colors telling you who is old, who is disturbed, who is still living fast. Ultraviolet picks out the newborns, bright and brash. X-rays light the atmosphere, the cavities, the shocks, the core. Layered, the bands stop being separate pictures and become facets of one object. The cluster resolves into a single, complex breath. Gas cooling and heating, stars igniting and dying. A black hole turning gravity into structure far beyond its size. Turbulence mixing, magnetic fields guiding, photons crossing a universe to make a coherent account. The jets remain the clearest testament to the unity of scale. Launched by physics that lives a whisper above an event horizon, they travel outward to change the fate of galaxies that will never know their source. Their touch is fine at launch, firm in transit, and broad in consequence. When they quiet, the core remembers. When they speak again, the core answers. Through them, the smallest and the largest converse, and the conversation writes itself into the light. We gather, old light, long traveled, gently telling us how a page was turned in the heart of Phoenix, and how the turning still echoes through the warm, bright sea. Out beyond the bright core, past the blue embroidery of newborn stars and the warm hush of dust, the Phoenix cluster is held within a larger pattern, an architecture so spacious it reads as quiet. Tens of millions of light years from edge to edge, a network of filaments stretches like pale rivers through night, separated by wide, low-tide basins we call voids. This is the cosmic web, the universe's scaffolding, drawn by the pull of dark matter over billions of years. Phoenix sits where those filaments meet, a radiant knot at a crossroads. From every direction, streams arrive gas, flowing in long, cool threads. Small groups of galaxies drifting like weather systems. Lone galaxies, falling with their own histories, folded inside. To understand the cluster, you let your attention widen until the local music dissolves into the deeper, slower rhythm that holds it. That rhythm began as a whisper. In the first moments after the Big Bang, quantum tremors were stretched to cosmic size by inflation, leaving some places slightly denser, some slightly thinner. Gravity likes a head start. Denser regions pulled in more matter and grew denser still, while the empty places gave up what little they had and became emptier. Time exaggerated the difference, and the universe learned the trick of structure. Filaments, sheets, and nodes surrounding seas of almost nothing. Billions of years later, galaxy clusters like Phoenix occupy the densest nodes, where multiple filaments converge and share their cargo. When astronomers trace the space around Phoenix, they find several highways leading in. The filaments are mapped in two ways at once, as chains of galaxies faintly glowing and as shadows in the spectra of background sources where intervening gas absorbs narrow slices of light. Follow those threads toward the cluster, and you watch matter descend a long gravitational hill. Gas drops in along the filaments and warms as it falls. Shocks marking the places where pace becomes heat. Small groups and solitary galaxies take the same roads, sometimes arriving intact, sometimes already tattered by tides. The deliveries do not stop. Growth is not an event, but a habit. The contrast between thread and void is stark. In the filaments, galaxy density may be tens of times the cosmic average. In the voids, it dwindles to a gentle scatter. Gravity did the sorting, but the results are ecological. Where matter collects, events accelerate. Where there is little, time relaxes. The Phoenix cluster, heavy even among heavyweights, reaches its gravitational hand across tens of millions of light years, tugging gently at the paths of objects that will not touch it for ages, and still feeling, in return, the pressure of the web that cradles it. Dark matter is the web's principal author. It does not shine, but its influence curves the paths of light from more distant galaxies, a phenomenon called gravitational lensing. Around Phoenix, background galaxies appear subtly stretched or skewed. With careful statistics, those distortions resolve into a map of mass. The map shows what intuition already guessed. Dark matter pools at the cluster and strands outward along the filaments. Visible matter follows the same pattern because it falls into those same wells. On the largest scales, the darkness writes the lines, the light colors them in. The filaments themselves are not sculptures, fixed and finished. They are rivers. Gas and galaxies move along them at hundreds or thousands of kilometers per second, accelerating as they descend toward the node. Kinetic energy converts to heat at the cluster's edge, helping to build the X-ray bright atmosphere that now fills Phoenix's interior. The process is old and ongoing. The current state of the hot gas and of its metals, mixed by turbulence and seeded by past starbursts, records the cadence of these infalls, the way tree rings remember seasons. Where the filaments meet the cluster, traffic thickens. Infalling galaxies sweep through the core at high speed and feel the bite of environment. Gravitational tugs from neighbors, tides from the cluster's central mass, and the steady headwind of the hot intracluster medium. Encounters rattle disks, tilt bars, and shear spiral arms. Gas is stripped from the outskirts first, then from the heart if the passage is deep and fast. Fuel pours into the cluster's atmosphere. Some of it later rains back as cooling filaments toward the central galaxy. Over repeated passages and mergers, spirals relax into ellipticals, their orderly rotation damped, their stellar populations mixed. Phoenix's gallery of smooth, red giants is not just a census, it is an outcome. On the other side of the pattern, the voids are not total absence. They hold thin air, diffuse gas, and small communities of galaxies that go a long time without bumping into anyone. In those wide spaces, evolution is unhurried. With fewer shocks and less stripping, galaxies can keep their gas and form stars for longer. The contrast between crowded nodes and quiet basins becomes an experiment. Nature runs at scale. Same physics, different neighborhoods, divergent fates. Location on the web is destiny's first draft. Computer simulations, starting from those tiny initial ripples and letting gravity do its honest work, reproduce the web's texture with astonishing fidelity. Run the clock forward, and filaments thicken, nodes condense, and clusters sprawl into the shapes telescopes see. Feed in different cosmologies, change the amount of dark matter or dark energy. Adjust the initial spectrum of tiny fluctuations, and the outcome shifts in measurable ways. Compare Phoenix and its surroundings to those virtual universes, and you test the deep parameters. How much matter the universe carries, how quickly space itself stretches, what kind of seeds inflation planted. The close agreement between observation and simulation is its own kind of lullaby. The reassurance that the laws we write down in quiet rooms describe a world that does what those laws permit. The web carries more than stars. The intergalactic medium, the thin gas that fills space between galaxies, threads the filaments like breath. It exists in many temperatures, some cool enough to leave delicate absorption lines in the spectra of distant quasars, some warmed to hundreds of thousands or millions of degrees as it slides down the filaments and feels shocks. By reading those absorption fingerprints, hydrogens, Lyman alpha, the traces of oxygen and neon at higher ionizations, astronomers take the temperature of emptiness, weigh densities too small to see directly, and measure how thoroughly star-forged elements have been distributed beyond galaxies. Around Phoenix, lines appear stronger and richer where filaments cross our sightline, a sign that the gas there is denser and warmer, as theory promised. What comes next for a cluster depends on the web that feeds it and on the larger frame that holds the web in place. The universe is expanding, not idly, but with intent. Distant objects recede faster the farther they are, a recession described by the Hubble constant. And for more than 2 decades, we have known that the expansion is accelerating, pulled by something we call dark energy, a pressure with the wrong sign for comfort. For Phoenix, whose light has been stretched by a redshift of about 0.6, that expansion is not just background, it is context. The photons we see left when the universe was about 60% of its current age, and have spent the time since climbing an ever-steepening ladder of stretching space. Dark energy composes the majority share of the universe's energy budget. Whether it is a static cosmological constant, an energy of empty space itself, or the slow roll of some field that changes with time, its effect on structure is clear. It pulls the distant even farther, future-proofing isolation. Gravity still binds what is already bound. Phoenix will keep its galaxies and hot atmosphere and dark matter halo, but power to the web at large will thin. In the far future, filaments will no longer feed the nodes. Clusters will become island universes, self-contained, their horizons shrinking to the limits of what they still hold. Between them, the night will stretch until even nearby structures fall beyond visibility, not because they have moved through space, but because the space between has grown too quickly for their light to cross. For now, the web still works. Infall continues. Filaments deliver. Phoenix grows by slow addition, by the settling of small groups, by the simmering of hot gas that occasionally drops out to fuel star formation and feed the black hole. The rate of delivery varies, thicker in some eras, thinner in others, depending on what upstream mergers have broken loose and how the web strands are braided. The cluster's recent history of cavities and cooling, of jets and blue light, is one chapter in the longer book of how a node metabolizes what the web brings. Lensing gives the dark shape. Dynamics give the motion. Absorption gives the temperature of space between. Put them together and the surroundings of Phoenix become a working laboratory. You can ask questions with details. How fast do galaxies stream along a given filament? Where do inflows shock? How far do metals travel from their stars into the intergalactic medium? How smooth or clumpy is the dark matter spine that guides it all? The answers sharpen not only the picture of this cluster, but the general recipe by which nodes feed and age. The web's design also governs how often galaxies within Phoenix meet. Strands deliver objects coherently, so infall is not rain but rivers. Galaxies arriving on the same filament tend to share velocities, and their orbits carry them through the cluster in aligned swaths. Interactions spark where those swaths cross the core. Some collisions merge, building larger systems whose stars then relax into smooth ellipses. Some near misses strip gas without joining stellar bodies, donating fuel to the intra-cluster medium, while leaving the donor lighter and quieter. Over time, the center's brightest galaxy bulks up by gentle cannibalism, while its satellites thin. Beyond the immediate, the web's gas continues to keep score. Its temperature tells you where gravity has done work. Its ionization balance tells you how the background radiation field pervades space. Its metal content tells you how thoroughly galaxies have bled their elements into the commons. In voids, the gas stays cooler, more pristine, less processed by shocks. Along filaments feeding Phoenix, it bears the marks of compression and heating, the fingerprints of a future cluster member not yet accreted. Project the present forward, and two fates bracket the possibilities. If flows persist for long enough, Phoenix will merge with neighbors, turning local superclusters into larger, looser associations, at least until dark energy's acceleration takes command and tugs those associations apart in the sense of communication, not binding. If instead the cosmic acceleration throttles delivery soon, the cluster will seal into itself, its growth by infall ending, its internal physics cooling, feedback, mixing left to right the remaining chapters. Both futures end with islands. The difference is how much time the ferries run before the bridges lift. Stepping back to the scale of understanding, the web around Phoenix is more than scenery. It is the reason a node like this exists, the reason it keeps receiving fuel, the reason its galaxies look the way they do. Each part of the cluster's identity carries a trace of where it sits. The abundance of old ellipticals, the presence of extended star formation along filaments, the chemistry of the hot atmosphere, the duty cycle of the jets set by supply. Study Phoenix, and you are also studying the web's logistics, the way the universe runs freight, from time's early warehouses to structures large enough to keep their own weather. Inside this context, even cosmology's most abstract terms grow personal. The matter density of the universe sets how tall the filaments grow. The Hubble constant sets how quickly distant walls slide outward. The parameters of dark energy set how long the roads stay open. Inflation's fingerprints appear in the power spectrum of small ripples that later became large structures. Match those fingerprints to the observed arrangement around Phoenix, and you cross-check the earliest story against the latest page. And still the telling stays gentle. Picture the cluster sitting at its junction like a city at river confluence, bridges stretching into the haze. In those bridges, caravans of galaxies approach, some proud, some ragged, carrying cold gas under tops of dust. Winds rise from the hot interior and slow their passage. Some cargo spills, some is delivered, some is transformed. Downstream from the confluence, the river widens, the water warms, eddies form, where bubbles rise from fountains in the square. If you scan the horizon, the countryside is empty, but not because nothing grows there. It is empty because distance has forgiven itself. Seeds drift there too, slower, quieter, blooming in their own time. The Phoenix cluster, in this frame, stops being an exception and becomes a sentence inside the paragraph of the web. Its outsized star formation is what a node does when supply overruns restraint. Its jets and bubbles are how a small engine speaks to a large room. Its hot atmosphere is the shore made from long deliveries of motion turned into heat. Its dark matter halo is the bedrock that set the course. And its future more building, or a long settling into sufficiency, depends on the same players, now dressed in the long robes of dark energy and expansion. Through all of it runs the grace of the same laws applied at different scales. Gravity folds and gathers, gas cools and warms, light travels and tells. What is left, after the details and names, is the shape of a process, tiny variations becoming filaments. Filaments, feeding nodes, nodes changing what they receive, and sending back signatures of their change into the wider medium. The cosmic web is both map and method. Phoenix is one bright point where the map thickens and the method declares itself plainly. Stand with it for a while. Let the lines of force and flow blur into a single texture, and you can feel how the universe makes large things patiently, with repetition, with no hurry, using only what the rules allow. Across the sky's deep ledger, galaxy clusters keep the books for cosmology. Count how many there are at each mass and distance, and the universe begins to confess its parameters. The Phoenix cluster, immense, luminous, improbable feeling yet fully lawful, lands as a decisive entry. For a system this massive to exist at a redshift around 0.6, the early universe must have seeded enough density growth. The matter content must have been ample. The fluctuations must have had just the right power on the right scales. Its very presence tightens the screws on theory, narrowing the ranges for how structure could have risen from first tremors to these continent-sized cities of matter. Its gravity tells us what shines is not what dominates. Weigh Phoenix by lensing, by the motions of its galaxies, by the pressure of its X-ray atmosphere, and the verdict repeats. Dark matter outweighs ordinary matter by several to one. Map the distortions of background galaxies into arcs and stretches, and you trace the invisible scaffold, a distribution that mirrors the luminous web because the light has obediently fallen into the dark. This portrait remains compatible with the idea of dark matter as slow-moving, weakly interacting particles that clumped early and then guided everything that followed. Test other possibilities, self-interactions, warm velocities, more exotic fields, and the cluster's statistics answer with constraints. Too much scattering would smear out the core. Too much free streaming would blur filaments. Too little mass would underserve the lensing scene. Phoenix does not settle the nature of the dark, but it moves the spotlight. Its timing in cosmic history is telling. We see Phoenix when the universe was roughly 60% of its current age, a season when star formation rates were sliding from their former crest, and mergers were less riotous than in earlier epochs. Against that trend, Phoenix flickers like a stubborn ember flaring bright, its central starburst roaring at hundreds of solar masses per year, its cooling flows surging while feedback stumbles. Outliers like this are gifts. They widen the envelope of what happens and insist that environment and timing can conspire to bend the curve of habit without breaking any laws. Astronomy is a time business. The light in our instruments began its journey more than 5 billion years ago. Since then, stars in Phoenix have lived and died. Galaxies have sunk toward the center or swung through and left. Jets have inflated and faded. Filaments have delivered fresh fuel and then paused. What we hold is a photograph of motion, a sharp still from a long film. The intrinsic delay is not a flaw. It is the feature that lets telescopes become time machines. Look deeper, and you look earlier. Compare frames from different distances, and the universe's evolution plays back in layered relief. Clusters like Phoenix will carry cosmology forward. Deeper surveys will find systems at higher redshift, pushing our senses back toward when the first large nodes condensed. Better mass measurements combining weak and strong lensing, hydrostatic profiles, and galaxy dynamics will shrink error bars on matter density and the amplitude of primordial fluctuations. Richer spectroscopy will refine temperatures, metallicities, and turbulence in intracluster gas, cross-checking models of how energy moves through plasmas. And detailed portraits of extreme clusters will show, with less ambiguity, how black holes pace the cooling and how starbursts ignite and fade. Gravity's theory shows up here not as a chalkboard claim, but as a glass-etched signature. Space-time curves around the cluster on scales of millions of light-years. Background galaxies become arcs, doubles, and distorted smears. Multiple images arrive by different paths with different delays. The shapes and positions of those lenses match the equations of general relativity with unnerving accuracy, despite the mass being spread rather than compact. These tests, far from black hole edges and neutron star densities, complement the strong field probes. Together they build a continuous line of evidence that Einstein's geometry remains the right language from event horizons to superclusters. Stand inside the idea of Phoenix, and the lines of connection thicken. Quantum fluctuations in the first instant, tiny patternless seeds were stretched by inflation into the faint template the universe later developed. Dark matter wrote the outlines of the web. Baryons, ordinary matter, flowed in, heated, cooled, and lit the pattern. Galaxies assembled. Black holes fed and spoke back through jets. Supernovae salted the gas with heavy elements that later cooled more efficiently, then formed stars more readily. Across 5 billion years of subsequent time, the accelerating expansion driven by dark energy shaped what could meet what, how rapidly supplies could arrive, how long the bridges of the web would stay open. Every layer touches every other. Nothing evolves alone. Phoenix is a convergence of extremes. Thousands of galaxies orbiting in a furnace of plasma heated to tens of millions of degrees. A central black hole weighing billions of suns, converting falling matter into light, heat, and pencil-narrow jets. A star factory churning at a rate that would look at home in the early universe. A cooling flow bold enough to outrun feedback, at least for a while. Each of these would be noteworthy on its own. Together, they form a single demonstration of how structure can, under certain alignments, surge past expectation. From this system flow lessons that travel well. Cooling flows, once mainly theoretical, here display themselves as physics rather than rumor. Dense cores radiating, gas condensing into filaments, filaments feeding stars and the nucleus. Feedback which so often succeeds in holding cores at bay, here reveals its delicacy. Efficiency depends on timing, on geometry, on how jet power couples to the densest gas, on turbulence and magnetic fields that can either distribute heat where it's needed or whisk it away. The plasma itself, thin, hot, magnetized, becomes a classroom for conduction, viscosity, and mixing in regimes no laboratory can mimic. Star formation in high pressure, high radiation fields asks whether the stellar mass recipe is truly universal or tilts top-heavy in extreme niches. Accretion disks near a supermassive black hole invite tests of relativity in the way their ion lines smear and skew. The jets, stitched from fields and rotation, show how energy at a horizon can guide matter across galactic scales. Transformation is the constant. Hot gas becomes cold clouds. Cold clouds become stars. Stars return metals and momentum to hot gas. Black holes pace the cycle. A cluster reconciles it all into a moving balance that is never still. The name Phoenix earns its poetry here. Rebirth from ash, not as myth, but as thermodynamics, radiative cooling, and feedback braided into a loop. Even the cluster's title on the sky ties modern analysis to ancient habit, the human impulse to draw meaning across darkness with lines of light. The photons that carry this whole story to us are fragile and faithful. X-rays cross space from the hot atmosphere and mark the cavities the jets carved. Radio waves trace the aging electrons that spiral along magnetic fields in ghostly lobes. Infrared light whispers of warm dust cloaking newborn stars. Optical light delineates the galaxies, their colors and shapes, a census of who is old, who is transforming, who is falling in. Ultraviolet picks out the hottest children of the burst. Put them together, and the cluster turns from rumor to resolved structure, from impression to inference. Instruments themselves marvels of polished mirrors, cold detectors, nimble arrays spread across continents, become extensions of our senses, tuned to wavelengths our biology never planned to see. Theory meets data at this boundary and learns humility. Models of cooling, of black hole fueling, of jet launching, of star formation, of dark matter dynamics, all sharpen their parameters against Phoenix's edges. When predictions match, confidence rises. When they fail, the failures are instructions. The extremity of this cluster forces clarity. Whichever explanations survive here will have the spine to hold elsewhere. The cluster's relevance reaches into fundamental physics by necessity. Temperatures of tens of millions of degrees. Plasma so thin collisions are rare, but collective behavior is strong. Gravitational fields shallow by black hole standards, yet deep by any other. These regimes are not simulacra. They are where our general laws must prove they are general. Phoenix is not just an object. It is a test bench. What lies ahead for the cluster and its kin will be drawn with finer strokes. X-ray missions prepared to map turbulence by line shifts will sketch the weather of the intracluster medium. Radio arrays that see polarization crisply will lay bare the magnetic architecture that collimates jets and ties bubbles to their borders. Infrared and millimeter instruments will track the coldest fuel cloud by cloud, filament by filament, measuring not only where the gas lives but how it moves and how it fragments. Time domain campaigns will watch the nucleus brighten and dim, linking changes in accretion to the growth of cavities years or decades later. Each increment in sensitivity and resolution deepens the portrait and leaves less room for vagueness. Yet the larger meaning remains steady. Among billions of clusters, Phoenix is a dramatic case, not a solitary miracle. Other systems show other facets. Relaxed halos that look like textbook equilibria. Colliding pairs whose shocks draw lines across space. Sleepy cores where feedback keeps perfect time. Together, they map the range of outcomes the same few laws permit. Variety is not a violation. It is a feature of a universe built from simple rules applied under changing conditions. So the story closes without closing. Phoenix stands as a bright proof that the cosmos is legible, that by counting and weighing, by listening across wavelengths, by drafting equations honest enough to be wrong sometimes, we can read what happened and what can happen. It also stands as a reminder that legibility does not diminish wonder. 1,000 trillion suns worth of mass, a sea of gas hotter than any stellar surface, a single engine turning gravity into jets that sculpt a room of plasma, filaments raining cold, stars igniting by the thousands each year. None of that becomes less astonishing because we can describe it. It becomes more so because description is a kind of touch. Hold one more image. The cluster as a lantern burning with old and new light, sending photons that cross a deepening, accelerating night to fall on a world where minds ask questions. The light arrives, we measure it, and the past speaks. In that exchange is everything astronomy promises, that distance can become knowledge, that time can be made present, that the most distant structures are still part of our circle of understanding. Phoenix will keep serving as a benchmark, a comparison star for the next generation of telescopes and theories, a steady reminder that the universe is both patient and dramatic. The lesson it leaves as we dim the lamps is simple and abiding. Order emerges, balance wavers, creation continues, and the laws are the same here, there, then, and now.